Okay, today we'll talk about chapter 22. This is the nucleophilic alpha substitution. So see this, if there is a carbonyl group, okay, and you have alpha carbon, I'm writing just one side like this alpha carbon, and it has hydrogen, at least one hydrogen or more hydrogen, okay? So what will happen if you take a base? So this base can abstract the proton from the alpha carbon. So here, let's say CH2 minus. Okay, this is the carbanion will form. So this carbanion formation is due to the stabilization of the anion by resonance by the carbonyl group. Okay, so it can form this resonating structure. So 2O hydrogen, O minus. Okay, and this is with the negative charge here. This is called enolate. Enolate. Okay. This can happen, a similar thing can happen under acidic condition. Okay. If you have an acid, suppose this one, so the lone pair of oxygen can take the proton, and this can form OH plus, okay, have oxonium ion. So the protonation is again of oxygen is again favored because of the stabilization of the oxonium ion by resonance. So this can form like this OH and carbon. Okay. So from this, in either structure, this one or this one, you can show that the conjugate base, here water, can take the proton, okay, and it can form this product. Or you can write directly here, and it can form this one, okay, which will make this one RCOH double bond CH. So see the similarity between this and this structure. Only you have here H and O minus difference. Okay. So as you guys know, this is called enol. So here in this structure, what do you see? That whenever there is an electrophile, okay, electrophile, I'm using the general term electrophile, it can be in different forms. So this electrophile can react like this generally, okay. So R, so you will be O and then CH2E electrophile. And here similarly you can show here the electrophile. This can come back and this will react with the electrophile and it will form CH2E. Okay, so this is called, so that's why this is called nucleophilic alpha substitution. See, this is carbon is the alpha carbon adjacent to the functional group. It forms a carbanion that is a nucleophile, and this hydrogen is substituted. Okay, so this is a substitution reaction. So now see the slight difference here. O minus here, because O minus is a better nucleophile. Okay, so here the electron density is more. So here you can see the enolate is a stronger nucleophile than the enol. Okay, so the enolate is a stronger nucleophile than enol. So in another word, another thing you can see, under basic condition you can make a stronger nucleophile, and under acidic condition the same enol will be a weaker nucleophile, and the difference you can see obviously via the negative charge. So I will give you guys example. So by changing different electrophile. So let's say here you have this molecule, CH3, and you take a base NaOH. Okay. So that will make the enolate, and you take an electrophile X. Okay, here what is X? Chlorine, bromine, and iodine. Halogens. Okay, chlorine, bromine, and iodine. So what will happen? So first it will make an enolate. So this will be replaced by the electrophile X. Okay. Again, sodium hydroxide. Here you see the sodium, the base behaves as a catalyst. Okay. So here again the sodium hydroxide will make another enolate because you have two more hydrogens. So it will be replaced by another halogen. Okay. Again another enolate. So all three alpha hydrogens will be replaced by halogens via subsequent stepwise reactions. Okay. But if you the same reaction acidic condition, here let's say suppose if you take acetic acid, okay, and bromine. See bromine, bromine or halogens. Here you take, see this one here. Suppose if you take bromine, then all you will have bromine. Okay. So under acidic condition, it will make an enolate, and the reaction will stop after substituting one hydrogen. Okay, this important point to remember. So because it is less reactive, it will stop after substituting just one hydrogen by bromine, the electrophile. Here it will keep on going. Now you see these bromines, the halogens are electronegative elements. So when you have a lot of electronegative elements on a carbon, on any atom, it becomes a leaving group. Okay. So I will take a specific example of bromine. Then when it becomes a leaving group, this carbon becomes a very strong electrophile. Okay. So under basic condition, let's say OH minus plus. So now the OH minus will react with this nucleophilic addition reaction. So this nucleophilic addition reaction, it will make O minus OH and CBr3. Okay, if you will take iodine, it will be Ci3. If you will take chlorine, it will be CCl3. So this will come back and this will leave. Okay, so what will be the product? So the product will be RCOOH plus CBr3 minus. So this will take proton. Okay, because it's a base, so it will make RCOO minus plus CHCbr3. Okay, What is this called? It is called bromoform. Bromoform. Okay. If you will take iodine, then it will be CHI3. It is called iodoform. If you will take chlorine, it will be CHCl3. This is called chloroform. Okay. In general, these are the halogens. So in general, this reaction is called haloform reaction. Okay. Do you guys remember this one? This was yesterday in the lab. Okay. For testing carbonyl compound haloform reaction. We did the organic 2 labs. So this is the reaction and this is the detailed mechanism. So what is the basic thing? If you have all three, see, to be another important point, remember, to become a leaving group, you need to have 3 halogens, okay? Then only it will be a leaving group. Suppose if you stop the reaction here, you have 1 hydrogen, only 2 halogen, this is not a leaving group. It will not leave, it will be as it is. Okay, or 1 halogen, it will not leave. Need to have all 3 halogens that will leave. So this haloform reaction, keep in mind, and the substitution with halogen on the alpha carbon, both under acidic and basic condition. Okay. So this another related reaction. If you take uh, an acid, okay, just acid, and it has CH2, see, acid functional group, okay. Generally, just acid, it has carbonyl though, acid, but because the carbon is not, this one, not that strong electron withdrawing group compared to aldehydes and ketones. So simply it will not undergo alpha substitution, no reaction if you take just bromine. Okay? But if you take bromine with PBr3, okay, PBr3. So what will happen? Then it will form alpha substituted product of Br. Okay. So how does you guys know that? See, let us see the mechanism for this reaction. You guys know that PBr3 is a brominating reagent of OH. So it will make CH2OBr. Okay. So in the presence of OH, enolate formation is not that feasible. It forms in rare cases, but it is not easy because this one is not an electron withdrawing group, the OH on carbonate. So what happens now after this bromine, because electron withdrawing group carbonyl, it forms an enol. Okay? Like this, enol. Okay, just ketoenol tautomerism. Because this is when bromine will react, it will form HBr as a byproduct. So HBr is an acid, it will form under acidic condition and enol. Then this one here will react with Br. So what it will form? Okay. And this after deprotonation will form Okay, this acyl bromide, okay, this bromide, see this one, is unstable. If you guys remember the carboxylic acid derivatives in the last chapter, just today you guys had quiz, that acyl chlorides are the most stable, most reactive, then anhydride, then thioesters, esters, and then amides. Okay, so these bromides are like the chlorides, even more reactive. Okay, so they're the most reactive. So if you will take water, okay, it will be hydrolyzed, hydrolysis. So this you will have Br, and this will be hydrolyzed OH. Okay. If you take methanol, so what will happen? What happens when methanol reacts with an acyl chloride? The question in the quiz. So alcohol reacts with the acyl chloride, it makes an ester. So in the methanol, the product will be brominated ester. Okay. So see these product from the intermediate. This is the intermediate of this reaction, and starting from here to here, okay, or here to this one is called HVZ reaction, Hell-Volhard-Zelensky reaction. Okay, so this reaction, you guys remember that carboxylic acid derivatives can be changed, that alpha substitution can happen if there is a alpha hydrogen in the presence of PBr3. Okay, and that bromine. Okay, any question? Similarly, if you carbon could be an electrophile. Let's say cyclohexanone. Okay, under a base. So remember, you need a under basic condition. There is a base like this one, widely used base. I'm giving you the structure. This. Okay? This, in short, it is called LDA, lithium diisopropylamide. It's a strong base. So what happened? It will take this one, this will form, okay? This basically it will form enolate. There could be several, many types of bases. Okay, just one common mechanism you guys remember, that you need a base to make an enolate or under acidic condition. So stronger nucleophilic enolate, so basic condition. Now if you take an alkyl halide, let us say the CH2I or Br or Cl, so what will happen? This will come here and this will substitute iodine. Okay. So it will make alpha substitution. Okay. So here, so under acidic or basic condition, okay, let's say you have here hydrogen. How many alpha hydrogens are here? 4. Okay, so it means all these 4 hydrogens can be exchanged with an electrophile under a basic condition particularly. Okay, so these are called enolizable hydrogen. Enolizable. So now if you take suppose sodium hydroxide catalytic amount, it will form a enolate, and you take D2O. Okay? So what will happen? It will, all the 4 hydrogens will be replaced by deuterium. So it's an enolate formation, just exchange, deuterium exchange. Okay. So this you guys keep in mind that so this is the deuterium, this is the enol formation, and then via keto-enol tautomerism, all the hydrogens will be replaced by deuterium. Now, suppose if you have 2 carbonyls, okay? See here on the same, I will show you guys. So how many here enolizable hydrogens? How many hydrogens alpha to the carbonyl? 6. Okay. So here this 2, here. So these are enolizable hydrogen. Okay. So based on the symmetry, these 4 are the same. Okay. And these 2 are the same. Now suppose if you take a base, so base NaOH, and what can happen if it takes this proton, then what will you get? See this one here, negative charge. Okay. This negative charge will be resonance stabilized. You can write one more resonating structure. See, this can come here, this can come here, this can go there. Or from here also you can write the another resonating structure. So here you will have double bond O minus. Okay. Now another situation, suppose if it takes this proton and it will make this anion. So see here, you'll have negative charge O here. Okay. This anion can be also resonance. You can write resonating structure. So what will happen? O minus. See the difference. Okay. So very important. Try to understand the resonance here. Can you write more resonating structure from this? No. If you write, it will go back here. So see, if you take this proton, then 1, 2, 3 resonating structures. If you take this proton, 2 resonating structures. So this one is much more favorable than this one. Okay, so here is the, remember, whenever, if there is a methyl groups, carbon that has hydrogen, and this carbon is flanked by 2 carbonyl groups, so this hydrogen is much more acidic than the other side hydrogen. Okay, this important point to remember. carbon having hydrogens flanked by two carbonyl groups are very, very acidic compared to only one carbonyl adjacent to the carbon having hydrogens, because of the possibility of more resonating structures. Okay, so such type of molecules that are generally, okay, if you have two carbonyl groups or two electron withdrawing groups, okay, here R are called active methylene compounds. What are they called? Active methylene compounds. So this carbonyl could be in the form of acid, could be in the form of aldehyde, could be, here you see R, if it is R can be hydrogen, R can be carbon, so it will make a ketone. R could be an acid or sorry OH, okay. R could be an ester, or they can be mixed, okay. And not only this, then you need to have ketone. If there could be other um, resonance stabilizing groups like CN. Okay, here you have ketone or both sides CN cyano, or you can have nitro, because nitro can also stabilize the anion by resonance. Okay, so these are the examples of active methylene compounds. In the book, we will there is a detailed study of two. Okay, acetoacetic and malonate. Okay, we will see the reaction of both one by one. So now let us see this one here. See this CH3 CO H H C O O E T CH2 CH3. Tell me quickly, how many enolizable hydrogens? Hmm? 5. See, 3 and 2 enolizable hydrogens. So which one will be the more reactive out of these two sets? You have 3 and 2, so these two will be the more reactive than these three, because they are flanked by, they have two adjacent carbonyl groups. So now if you take sodium ethoxide, a base, okay, so what will happen? It can take the proton and it will form negative charge. So you'll have CH3, CO, hydrogen, negative charge. You can write all types of resonance for this. I'm short writing ET. Okay. Now if you take an electrophile, let's say here allyl bromide. So what will happen? This is a very good nucleophile to react with this. Okay. So here what it will form, CH3, CO, C, H, O, E, T. Okay. Now you see still you have one more hydrogen that can also be replaced by repeating the reaction. So sodium OET minus, here you'll have this, it will go, so you have CH3, CO, carbon COOET, you have allyl. Here, negative charge. Take again, as I said, that you repeat the reaction with allyl bromide. So, okay. So what will happen? CH3CO OET. So both the hydrogen is replaced by two allyl groups. Okay. I say this one, both the hydrogens are replaced by this allyl group. So after replacing both the hydrogen, OET, so you have this. Now reaction with an acid, okay, under acidic condition, water. And if you heat it, what will happen? Say this reaction, remember. What happens when an ester is reacted with water under acidic condition? What is the reaction? Last chapter. Yesterday you guys had quiz. Ester reacting with an aqueous acid. It's a hydrolysis. Okay. Ester will be converted into an acid. Okay, this is the acid. Okay, ester hydrolysis under acidic condition. Now next step, what will happen? See this here it is heat. Under heating condition, what happens? This will come here, this will go here, this will go here. So what will be the product? Right, quickly, I will give you guys two